Okay, let's start again. The next speaker we have is Julian Berman, and he's going to talk about building an interpreter in RPython. So, Julian Berman.
Hi. You guys hear me okay? Cool. Enter, right? So this is a talk that I gave as a 4-hour training session at PyCon Italy last month. So it's been trimmed down significantly. We're really basically only going to cover sort of high-level stuff, but my overall goal is sort of to interest you enough to either check out the full tutorial, which is at the end of the slides, if you really want to go through the whole thing and actually build something. Excuse me. Or to just interest you in general in the high-level stuff, because it'll help you, I hope, in understanding interpreters that are built in this way, including PyPy most notably. So I'm going to start from scratch, basically. So assuming no knowledge whatsoever of interpreters, compilers, anything like that. And I'm not an expert on any of these topics. So I just find this fun, and I find it accessible if you actually just get past the initial stages. So let's see. So first of all, I work in New York for a company called Magnetic. We're in ad tech. We do high-volume stuff with PyPy, lots of requests per second. Have an office in London. Feel free to come talk to me about all of that fun stuff later. So let's just get started. So what's a program? So the reason why I'm starting here is just to set a little bit of context. So programs at the most basic level are very simple. They take a bunch of input and they produce some output. They do some computation in the middle, but that's all. So maybe your program is Google Chrome.app, and maybe your input is an address bar, which is too small to see, I hope. So you type some stuff into the address bar, and then out pops some output from the program, which is a rendered python.org homepage. And every program conforms to this sort of model. Whatever the input actually happens to be, whatever the computation that happens in the middle, and whatever the output happens to be. But I'm sure most of you know, computers don't execute text. Computers execute executables, and executables are sort of streams of instructions that the computer knows how to execute. So you have whatever program that you wrote in whatever fun language was popular when you wrote it. And then there's some process for actually translating your program into an executable that your computer actually knows how to run. And then it's that executable which actually is taking in your input and spitting out your output. So interpreters and compilers. Just get rid of that title bar there. So interpreters and compilers are just programs. And sort of the whole lead up here is just to make that very explicit, which is that there are programs called interpreters and compilers. The difference between them isn't really important for the moment, which basically take source code and translate them into something that you can actually run. So an interpreter is a program. It takes as input some source code written in a language and produces as output the execution of that program. And then either it does that by sort of directly translating it into something that the computer can actually execute, or it does it by translating it into some intermediary form, which then executes on some fake computer or virtual machine. So before we talk about building an interpreter, let's talk about some interpreters that we know already. So CPython, aka what you get if you type Python and didn't specifically ask for something else. So CPython It's written in C, right? It's a program, has to be written in some language, it's written in C. Bytecode compiler and stack-based VM. So bytecode compiler means basically takes your source code, converts it into bytecode. Bytecode is like machine code, except it's not. It's some made-up, simple language, which we'll see a bit more of in a second. And then a stack-based VM we'll see more of later. But roughly, there's some model for how this actual interpreter works. It converts your source code into bytecode, which is something like machine code, and then it takes that bytecode and executes it on a virtual machine, which is something like a CPU. And the CPython VM and implementation is designed to be sort of simple in its implementation. It's fairly readable. You can just open it up. The relevant file for sort of later on in this discussion is ceval.c. If you just open it up, there's a whole lot of stuff that you can just read from top to bottom in there. So here's the diagram. Your input is source code of your program. There's some intermediate step where it gets turned into bytecode. Sometimes it gets saved on disk. And then that bytecode actually executes on the CPython VM. So this is too small to see, which is fine. It's not meant to be seen on the right. So on the left is some Python code. It's not terribly useful, but it's just for demonstration purposes. So very simple function. It takes two things, and if x is greater than y, then it adds them. Otherwise, it subtracts them. And on the right, like I said, you probably can't read that very well, but I will read it out loud, at least in part, is the output of the dis module. So if you've ever looked at the dis module, basically, it's a module that knows how to take objects, code, whatever, and spit out what bytecode it corresponds to. So this actual Python code on the left translates into some bytecode on the right, which the most interesting parts are, so there's this load fast bytecode, which means give me the value of some actual variable. So there's x over there. Go find x's value and put it on the stack. So stack is a stack. And then does the same thing for y. And then it calls this bytecode called compare op, which means take the two things that are on the stack, pop them off, compare the two of them. If the left one's greater than the right one, then push true onto the stack. Otherwise, push false onto the stack. And then it says pop jump if false, which means skip the middle block if it's false. Otherwise, execute the middle block. And so it goes on and sort of finishes this execution, very much parallel or closely paralleling what's going on the left side, but in more simplistic terms that are manipulating a stack, hence stack-based VM. So again, before we talk about actually implementing one of these, so PyPy is the foremost example of an interpreter written in RPython, which we'll talk about in a second. It's, again, a bytecode compiler and a stack-based VM. So it has the same general execution model as CPython in that it takes Python code, converts it into bytecode, and then executes that bytecode on a VM. Implements the same language. So now let's talk about RPython. So what is RPython? So originally, RPython was just the language that they used to write PyPy. And it's increasingly become sort of more I'd say widely used. There are other interpreters that use it. Topaz is a Ruby interpreter that uses it. We're going to write a little small one in the next however many minutes. So what is it? So RPython stands for restricted Python. And what it is basically Python with some restrictions. So it's a strict subset of Python in the sense that anything that's valid RPython is valid Python. You can execute it on any Python VM that you'd like. And when you execute it on a regular Python VM, you're executing it in the same environment as any other Python code that you would execute. So for example, if some RPython code ends up raising an exception, you'll get that exception in a traceback when you execute it on a Python VM. The same nice things might not actually happen when you do other ways of actually executing RPython. And those other ways are actually that it's amenable to annotation and translation. So what does that mean? It means you take some RPython and you basically give it to the RPython toolchain and you say, now give me something else out of this. And that something else is machine code or an executable. So it's a restricted enough subset of Python where the toolkit, our Python toolkit, is able to actually take the code that you wrote and figure out what all the types are, and then after that, be able to produce you an executable, whereas doing that for Python code, which is arbitrarily dynamic or all sorts of fun things going on, isn't as easy, or it's impossible, or yeah. So how is it restricted? Just in brief, it's restricted, it's statically typed. So that just means you can't change the types of variables. So if you declare, not declared, but if you set some variable to be something of a certain type, you can't change it after. And also, you can't put different types inside the same collection. There has to be some way of actually unifying the types. So you can't have a list with the string cat in it and the number 12. Because strings and integers don't have a common base type, because object doesn't count in RPython, basically. So there has to be some way of actually unifying the types that you put inside your collection. So obviously, the goal here is that it's giving you the tools to actually do the second thing, annotation and translation, producing an executable for you. And in order to actually get those goals, you're giving up some of the things that you would otherwise have in Python. You still have the general syntax of Python. In fact, everything that we're going to see just looks pretty much like regular Python. But you will notice some differences or some things that look slightly weird if you're writing regular Python, because you just can't do them in RPython. Two things represented here as pictures, which RPython also gives you, which I basically won't mention other than this. So when you write things in RPython, the reason why it's particularly good for writing interpreters is it has all sorts of garbage collectors that you can just plug into your interpreter. So you don't have to worry about memory management for whatever language that you're implementing using RPython. And also, it has tools for instrumenting the language, the interpreter that you're writing, in such a way that it can bolt a JIT onto your interpreter. And I won't talk too much about that either. I won't talk at all about that. But it's magic fast sauce for your interpreter. So in, let's see, 13 minutes. So let's take something exceedingly simple, no control flow, no real anything exciting. We'll show basically the extent of what we'll implement here. So we're going to basically take a very simple language and implement or show the steps that would be necessary in order to implement it using RPython. So on the left here is some representation of this language that we're targeting or just sort of playing with. It looks obviously sort of similar to Python, but there's really nothing there. So all we're showing here is sort of adding integers, adding some strings, and then outputting the two objects there. But that's sort of a rough outline, if even that, of what we want to actually interpret, right? So how do we get there? So there's 3 steps. We'll go over them briefly, each one, but roughly the way that we actually are going to be able to get this code to do things is we need to take this string and somehow be able to interpret the instructions that that source code is trying to make happen. There's a bunch of different ways that you can actually do that. The simplest for me is this 3-step process, which is very similar to the one, well, it's the same as the one that, that we mentioned for PyPy and CPython, which is, first we're going to parse the strings into an object representation of what's going on there, an AST, if you've seen those. Then we're going to compile that AST into some bytecode, same as the way PyPy or CPython would compile an AST into bytecode. And then once we have that bytecode, which is just going to be a stream of bytes, integers, excuse me, then we'll write our stack-based VM that just manages to implement executing those bytecode. So I'm going to start in the background here before we go much further. So I have here another interpreter, not the one that I'm going to demo, only because it's slightly larger. And I'm going to start in the background here, this tool here called RPython, which is the entry point to the RPython toolchain. And as we go through the steps in the background, this will run and hopefully pop out an executable for us. So what this is going to do is take this thing that I'm pointing it at, which you may or may not be able to see. I'm not going to bother messing with the window here because it's going to mess with the full screen. But I pointed it at a file which happens to be valid RPython. I'll show some of what's in that file and others possibly at the end. So I'm pointing it at this file, which is some RPython, and I'm telling the toolkit to please compile this RPython into an executable for me. So I'll start running this in the background. It's going to do lots of things. And hopefully when we come back at the end, it should be done. Oops. So, so step one, we said we'd like to take this source code representation on the left and actually convert it into an AST. So what's an AST? You may or may not have seen one before. It's a programmatic representation of the text that you see on the left, right? So it's a tree, and it's trying to be a sort of slightly easier to work with representation of the source code. So text is hard to manipulate, it's hard to execute directly. So the first step is sort of taking the text that we have, which is literally those characters on the left, and converting it into something that we're going to be able to work with using the normal methods that we know how to work with things, objects, basically. And so that top line over there, which is trying to assign the output of 2 and 7 to some variable, we'll represent using this AST on the right. So it's fairly self-explanatory, I hope, how the right comes from the left. We have an assignment statement. We're going to have this object called assign, which we'll write, which we will write. It won't be up on a slide, but basically it will have the name of the variable that we're actually going to assign to, and then the right-hand side, basically. So it's left-hand side, right-hand side. And on the right-hand side, in that first line, we have a binary operation. It's the plus operation. And then the operands for the plus operation is an integer literal and another integer literal. So that's what we want. And of course, we want similar, extrapolated results from the last 3 lines. So for example, the second line would be quite similar. Just replace the variable name and replace the integer AST nodes with string AST nodes. The bottom ones will be a little bit different. Those would look like some sort of function call AST node that took the name of a variable or a constant or something that you were going to pass as an argument to the function call. So how do we do that? So again, like everything in this entire domain, there's many ways to do it. Please don't be flustered by the amount of code that will now appear on the slides. So you can't use whatever random Python library that you'd like to do all these things, because our goal, remember, is to actually have valid RPython, which means your arbitrary Python library won't necessarily satisfy whatever constraints RPython has. So it may work, it may not work. So for things that are actually directly related to developing interpreters, there's often or occasionally existing RPython libraries that you can use, which actually will help you get the job done. So for example, how many people here are familiar with Ply? couple. So, or yak or any of these things. So basically, ply and yak, there are others, are tools, not for Python, well, Py. They're tools for basically creating parsers. They're called parser generators. So it's a tool that basically lets you define programmatically what some rules are for actually parsing some text. And it will construct for you an object that knows how to then parse that text and produce your output. So let's go through this slightly slowly. This PG equals parser generator, I've omitted the actual arguments there. They're not that interesting. So that's the object that we're going to be using. It's a parser generator. We're going to tell it basically some rules for how we actually generate, or for how our language looks, basically. So what does this mean? So this line here is sort of the key. It's a decorator called pg.production, and it has this weird syntax in there, expression colon, expression plus expression. So if you're familiar with eBNF or context-sensitive grammars or like any of those things, then you can probably guess what that is. If you're not, here's the 3-second description. So we're saying basically that in our language, or in our parser for our language, we're defining that an expression can be produced whenever you have some expression and then a symbol, the plus symbol, and then another expression. So you're telling the parser generator, here's a possible rule for when you would have a binary operation. It's any time that you see an expression, the plus sign, and another expression. Now, this isn't a complete example. You also need to tell it some base case that it would know, like, by the way, an expression can be an integer or a string or whatever simple expressions your language would have. It just didn't fit on the slide. This is enough already. So you can imagine another rule that would say an expression is a number. And you'd have another function that basically would be responsible for handling that case. So what's going to happen here is that anytime that your parser will see expression, then plus sign, then expression, RPy, the library, will call this function and pass in this object, which is roughly a list of semi-parsed tokens. So it's going to pass that into this function, and you're free to return whatever you'd like as the result. And so you use these decorated functions in order to actually produce your AST. So here you're saying, this is what an expression is, and when you see it, give me back a binary operation object, which I've managed to typo at the top there. Sorry about the name error. Excuse me. So give me back a binary operation. The operation is going to be P1, which will be, so this will be P0, P1, P2. It's just a list with 3 tokens inside of it. So the operation will be P1.getStir, which means basically just give me back the text of what was there. So you could just inline plus here because we don't have multiple operands, but it's a bit more realistic to have the same function, let's say, handle subtraction and division and multiplication, in which case you actually need to know what was in there. The left side of the binary operation is going to be whatever was the left side there, and the right side is going to be whatever was the right side there. And that's it. So from there, RPy knows how to basically parse things that look of that form, including recursively, and give you back this AST node, which you define, which we've defined above, called base operation, called binary operation, and it will give you back a tree, which was the result of actually parsing your structure. Make sense? Nods? Cool. How much time? Only a minute if I actually want some questions. OK, so let's go a little faster. So that was step 1. Now we have an AST. If we actually want to interpret things, now we need some bytecode. So here's how you take AST nodes and now tell them how to compile themselves. So let's take that same AST node binary operation and give it a compile method, which we're going to end up calling. We're going to need some place to hold state because as you're compiling a program, there's going to be things that you need to keep track of. So we'll have some object, which you can just imagine as a bag of state that you can throw stuff on. So how do you compile a binary operation? So ultimately, what we want to produce is going to be, give me the value of the left thing, give me the value of the right thing, put those both on the stack, and then put a third bytecode on there that says what to do with those first two that we put on there. So the way that we get that is we tell the left thing to compile itself, we tell the right thing to compile itself. You can imagine if these were integer nodes, the way they'd compile themselves would be by just saying, put a load fast operation on the stack, which means get my value. So you'd end up with load fast for the left, load fast for the right, and then emit a bytecode for my operation, which is the binary add operation. So you can imagine if you had subtraction, and then you saw a minus, you'd emit binary subtraction. And so this compile method will actually emit the correct bytecodes for loading the left value, loading the right value, and then performing the operation that pops those off and puts the result back on the stack. And you do this for all of your AST nodes. You basically teach them all how to compile themselves, for the higher level ones by calling down into their children, and for the leaf nodes by just doing whatever bytecode instruction actually corresponds to loading them. And when you do that for all of the AST nodes, you basically will end up with this stream of bytecodes that you can now execute. And so let's run it. So you can imagine that you end up with this stream of bytecodes like we saw before. Maybe now we're loading a 2 plus 7 like we had in the first example. So we're going to have a bytecode that says load the constant. Now that 0 is an index. It means we're going to keep basically an array of constants. So we'll have an array that says 2 is the first constant, 7 is the second constant. That's how Python does it as well. And so we're going to have a loop. And the loop is going to basically keep track of where we are executing this stream of bytecodes and perform an operation depending on which bytecode we see. So if we see a load const, we're going to put the value of that constant onto the stack, which is the implementation that we want for that bytecode. And then if we see binary add, which we will at the end, our implementation is going to be exactly what we said, which is pop the top 2 values, add them, and put the value back on the stack. And this is really it in the obviously very simplistic case, because now what we have is we have an AST node that we can parse out of addition expressions. We have AST nodes that know how to compile themselves and produce bytecode based on whatever you put inside them. And now we have a bytecode loop, even though there's no loop at the top. But we have a bytecode loop that's basically going to sit there, evaluate those expressions, and execute the appropriate stack operation depending on what operation was there. And that's it. It's obviously not it, but that's it. So that link on the bottom over there is the full tutorial, which you can go through from top to bottom. There's also example interpreters that are linked from there. Slides are up in various places. I don't know if we have time for questions. 2 minutes? Yeah?
Hey there. How good is the RPython documentation? Because when I've looked for it in the past, there was almost none.
What's your name?
Ian.
Ian. How good is the RPython documentation? So given that you said in the past, I will say better than it was. It's not great, but so to me, the problem with RPython used to be the error messages more than the documentation. So like, the documentation wasn't great, and it's still not fantastic, but when the documentation is not good and I can't figure out what the error message means, then I'm really in trouble. And that actually didn't happen to me the last couple of times that I tried, and I don't think it's because of experience. I think actually they've improved the tooling to be a bit more friendly. So better, I think, is the answer.
Is there a good tutorial there?
A good tutorial?
is that the tutorial?
Try it and let me know. It went well in Italy, so yeah. Anybody else? Cool.
Okay, thank you so much.